In this lecture, we will see displacement gradient tensor and strain tensor and relation between them. So let's see displacement gradient. So this is basically the gradient of displacement vector. We know displacement is a vector. So let me give the background first. Okay, we know temperature, right? So temperature we know is a scalar. So I'm trying to explain like why the displacement gradient is a matrix. Okay. So let's take no temperature which is scalar, and we know we can compute the gradient of this temperature delta. This is called no delta. It's Nabla operator, and we can say grade T. We can read it as grade T. So grade T is equal to dou T by dou x. Okay, I dou T by dou y j dou T by dou z k. So when we find the gradient of scalar temperature, okay, we get three components. So gradient of scalar becomes a vector. So here why so okay, gradient of scalar why it is vector. We know like no, when we say gradient, okay, we attach a direction to this scalar. Okay. We say like okay, temperature varies in x direction this way, temperature varies in y direction in this way, and similarly temperature varies in z direction in this way or this magnitude. So that is the reason the gradient of scalar becomes a vector. Similarly, when we find the gradient, okay, of any vector, for example displacement. So displacement is already vector. So when we attach gradient, we put additional vector or we attach one more vector on top of this vector. So we say okay, gradient of displacement vector is like how no, u is changing in x, u is changing in y, okay, and u is changing in z. So this is display. This we can say gradient in of the first row is gradient of x displacement. Similarly, we say okay how displacement in y that is v. So displacement in y changes in x direction, displacement in y or y displacement changes in y direction, and how y displacement changes in z direction. Okay. So this is the second row is gradient of displacement or uh, gradient of y displacement. Similarly, this is a gradient of z displacement. So we are putting vector on top of vector, and that's how we get tensor. Okay. And that is the reason we get no, displacement gradient as a 3 by 3 matrix. Now, this displacement gradient, okay, we can decompose into two different tensors as given. Okay, if you do a summation of these two matrix components, like for example, this component plus this component, we get dou u by dou x. Similarly, this component and these components, when we add, we get dou u by dou y. So this way, we can decompose it into two different tensors. And if you notice this, this one is a strain tensor. Okay, I can say this is epsilon 1 1, this is epsilon 1 2, this is not gamma 1 2. Okay, this is epsilon 1 2 which is equal to gamma 1 2 divided by 2, and this is epsilon 1 3 which is gamma 1 3 divided by 2. So this is similarly this is epsilon 2 1, epsilon 2 2, and this is epsilon 2 3, epsilon 3 1, epsilon 3 2, epsilon 3 3. And this shear components, uh, here the shear component is twice, I mean, shear strain divided by 2. Okay, this is just for convenience, okay, or so that we can decompose. So strain tensor always uh, will have epsilon 1 1 and epsilon 1 2, not gamma 1 2 divided by 2. So you can understand the reason. The only reason is that convenience. Okay. And if you see this tensor, this is our rotation tensor. This is omega 1 1, omega minus omega 1 2, minus omega 1 3. And this is minus omega 2 1. So we can say my plus omega 1 2. This is omega 2 2. And this we can say minus omega 2 3, which is equal to plus omega 3 2. Similarly, this is omega 3 1. This is omega, this is minus, this is minus omega 2 3. This is plus omega 2 3, and this is omega 3 3. So we have omega 1 1, 2 2, and 3 3 0, because we cannot, there is nothing like a rotation in 1 1 plane. Okay, you need two axes, okay, two perpendicular axes that makes a plane, and we can find the rotation in that plane. So this one, there is nothing like plane called 1 1 or 2 2 or 3 3. So these rotation components are 0. Okay, and when we add all the components, we get displacement gradient. Okay, so we can write no, nabla or grade uij, which is displacement gradient, equal to strain tensor. This is in matrix form. This is actually tensorial notation. In matrix form, we can write all nine components of strain tensor and rotation tensor. Okay. So we can say in general matrix algebra or linear algebra language, we can say this is symmetric and this is skew symmetric matrix. So given any matrix, okay, for example A, okay, if we split it something like this, 1 by 2 A plus A transpose plus A 1 by 2 A minus A transpose, we can split it into two different matrix, and this first one is symmetric matrix always, and this is skew symmetric. Symmetric means all the off diagonal components are no, omega ij, sorry, epsilon ij is equal to epsilon ji. Okay, and skew symmetric means omega ij is equal to minus omega ji. Okay, so once we find the displacement, and from that we find displacement gradient, we can easily separate out our strain from this displacement gradient, and we can also separate out rotation, which is rigid body rotation. Okay, so reason is that when we have displacement gradient, okay, it is it it doesn't produce any strains only. Okay, it will have some rotation, rigid body motion terms as well. So that's why, that is the reason we need to separate out into strain tensor and rotation tensor. Now we can say like, okay, this strain tensor, okay, this strain tensor is responsible for generating strains, or this is actually measure of deformation, whereas this rotation tensor doesn't produce strains, because this is rigid body motion. This is the measurement of rigid body motion. This is how we compute displacement gradient, and from displacement gradient we can split into strain tensor and rotation tensor. So just for no example, okay, for example, let's it is very simple mathematical operation. Let's take some matrix is given 1 2 3 4. Okay, let's take this is a displacement gradient just for example. Let's say this is grade A. So we can find A and A transpose. So A transpose is 1, 3, 2, 4. Okay. So the first symmetric matrix, which is a strain tensor, is equal to 1 by 2 A plus A transpose. Okay. So we can find 1 plus 1 divided by 2, 1, 4 plus 4 divided by 2 is 4, 2 plus 3 divided by 2, 2.5, and this is 2.5. And we can see this is a symmetric, okay? This is a straight tensor. And similarly we can find skew symmetric component of this matrix A, okay, grade A, as 1 by 2 A minus A transpose is equal to, firstly these components will be 0 diagonal components, and 2 minus 3 divided by 2 is minus zero point 0.5, and 3 minus 2 divided by 2 is zero point 0.5. So this is, we can see, skew symmetric. Okay. So given any matrix, so just no, the purpose of this showing this calculation is that we can easily compute no, skew symmetric and symmetric component of matrix, and in computer it is just one line of code. Hope this makes sense. Like no, now we can understand or differentiate the difference between displacement gradient tensor and strain tensor. So the gradient, displacement gradient is not always strain tensor. Okay, it is including strain and rigid rotation components.